Okay, we have done mechanical properties. Today we go into strengthening mechanism. This one will be in your final exam question. Because your test 2 will be phase diagram and either polymer or ceramic or composite material. Okay, today we look at how to make the metal become stronger. We look at diffusion. Diffusion means we spray something on the surface by using temperature, make it become stronger. Okay. So first is diffusion, as what you learn in your chemistry. If you drop a drop of ink or salt paper or salt into the solution, you will see the spreading of the molecule. For example, the one you see on the screen here. If you drop a dye, you see the dye red color, it was dispersed, and when it becomes stable, you will see the red dot disperse equally in the solution. Okay, so this one is in water. However, in material, in the metals, it will behave similarly. And if can, you follow the Ohm's law, the HR law, the Ohm's law, that the size must not more than 15%. The crystal structure must same. The electron valence must be same. No chemical reaction happen. This one, all this must fulfill. Okay, so this one you read. There's a process called diffusion. Means diffusion is a phenomenon of material transport by atomic motion. It's in the atomic scale. Okay. So in metals, we'll use illustration of diffusion couples. So here we only show you by using two type of material. In the real application, you will have more than one materials. You mix nickel, you mix carbon, you mix different types of titanium and all this together, it becomes strong. So let's say you have two types of materials, copper and nickel. You put side by side. Right, copper looks something like this color, right? And is yeah. Then nickel is very small, right? So this one is before high temperature, before heat treatment. You look like this. So we will draw schematic presentation of copper and nickel. Red color represent copper, color represent nickel. So when and then there's a graph there to just to represent the concentration versus position. Concentration versus position. So if on the left hand side you see 100%, on the right hand side you also see 100%. So you'll see copper 100% until the middle point. When you reach middle point here, the copper drop to 0% all the way to the right. Same with the nickel. On the right, 100%. Move to the center, you will drop to 0, and then 0 all the way to the left. So this is a concentration graph between the two material at room temperature or before heat treatment. So after heat treatment, what do you think the graph will be? What will you think the graph will be when there's a mixing or diffusion happen? What happened to the graph? What happened to the graph? We have two material. What do you expect? What happened to the percentage at the when it reach middle if you are the red color? Will you do like that? Or Will you do like that? Or will you do like that? Or will you do like that? Which one? If you slowly, you increase the temperature very carefully. What do you think? Okay, try to think. Okay. So when you heat it up, right? You heat it up, the diffusion happen. So copper will go into nickel, nickel will go into copper. Okay, this is on the left diagram. What about the schematic presentation? The red will go into blue, and they will exchange position. Right, they will exchange position, and the graph will look something like this. You will go 100%, and then you will slowly, in a curve form, and reach 0%. Okay. Now, copper and nickel can do this behavior. We are assuming their radius or diameter will be almost same, so that they can switch place very easily, right? Like this. Okay. So this process, atoms of one metals diffuse into another, is called interdiffusion or impurity diffusion. Okay, if you have two elements that mix together and you interchange location, you call interdiffusion or impurity diffusion. So there is a net drift or transport of atoms from high concentration to low concentration. So from high to low, from high to low, it will be like pressure principle. You move from high concentration, move to low concentration. So copper will move from the left to right. Nickel will move from the right to left. So from here, you see diffusion also occur in pure metals, but some atom exchanging. So it's called self-diffusion. So the slide just now is two different materials. We call interdiffusion. So if it's a pure, it's called self-diffusion. So as you can see on the diagram from the left to right, so you see that there is a missing space here on the dot here. So this dot move to the left. Okay, move to the left. So you will see actually the atoms, the one highlighted, move to the left. But what is the motion that you see for the whole? The whole move from right to left. So the atoms, the diffusion happen from left to right. The atoms move from left to right. However, the hole or vacancy move from right to left. Okay. So this one, diffusion also can happen when the impurity or the atoms outside the cubic cell go and replace the things. Then this one was kicked out. This also called diffusion. So like what you learn in the defect or impurity or imperfection, there are two. Interstitial and substitutional. Means you can substitute or you can jump inside the space. It's called interstitial. This one in the defect chapter. So there are two. Now we look at the rate. How fast the diffusion happen. Okay. So here on the graph here, we look at energy. Okay, the energy and the coordinate or the location, reaction location. So here, this is just a presentation. So there are three important energy here. Reactant energy. The P here is a product energy. The E star here is you can say as an activation energy. So there are three parameters that we will use for the rate of process. So we three EF reaction, so ER reaction, EP products, E star is activation energy. Okay, so this one you go up and then go down. When you reach EP, you already get the end results already. Means the final products. For the diffusion to happen in metals, you need to give it energy. You need to give it energy from a reactant. Give it energy, then you go to activation. After activation, it will drop down. So energy will release to reach the final products. Oops. Okay, so here, activation energy is the region above the reactant energy. It's the additional energy required above the average energy of atom is called activation energy. So RF, ER here is a stable energy. So if you want to mix, you need to give energy. So from this line on the above, maximum energy, then it drop down. So the amplitude here is activation energy. Okay, so atom energy level, energy of reactant. Then if you go up, the reaction is exothermic because energy is given off in the reaction. So here is called exothermic if we go up. Right? Exo means it gives energy. Then this one will have sufficient energy to react spontaneous. All right, this one is the energy of product. So this is just a highlight. At any cases, there's only a fraction, means a few percentage of the material will reach E star or will reach the activation energy. So Boltzmann, there's a Boltzmann model. He studied the effect of temperature. What happens if you have the molecule? So we have this equation. Probability of having diffusion or activation energy will linearly with the exponential E negative E star minus E stroke KT. Or you write in the linear equation, there's a K here. So Boltzmann constant. Boltzmann's constant have two types. One is in Joule, one is in EV. So here we use Joule because we link with the energy here. Right. So give you the equation. So the fraction of atoms or molecule in the system having the E star or having activation energy will give you by this equation. N divided by N total. N is number of small n is number of atom molecule with energy greater than the E star. N total, capital N total is total number of atom or molecule present in the system. So this one is number of Avogadro, or we calculate the mole, how many mole of that, then you multiply by the number of Avogadro, you get N total. Okay, so Boltzmann constant here, you see, I'll give you another one. Boltzmann constant here is in EV over Kelvin. So just now is in Joule, so it depends on the parameter you use here. Just want to highlight the temperature is in Kelvin, not in Celsius. N divided by capital N total equal to C. C is a constant value determined by experiment. So here we look at number of vacancies at equilibriums. So just now you see how the hole or defect move if you have diffusion. So you compare side by side. You compare side by side. The equation to calculate vacancies and the equation of probabilities of energy with molecule or atom with energy greater than E star. You compare side by side, actually they are almost same. So NV divided by N equal to CE exponential minus EV divided by KT. This one you learn in the defect chapter. But you compare side by side, the differences here is E star minus E stroke divided by KT. But for calculating the number of vacancies, you take EV instead of E star minus E divided by KT. Huh? So just put side by side so you observe the differences. Don't use the wrong equation when you solve this kind of question. The one that on the left is for diffusion chapter or chapter 5. It asks you how many atoms that having greater than E star. The one on the middle, NV here is number of vacancies. Okay, number of vacancies. So how we apply the equation? So calculate the equivalent numbers vacancy per cubic meter in the pure copper at 500 degrees C. The second type is ask you vacancy fraction at 500 Celsius in pure copper. A same energy formulation is given. C assumed as 1, Boltzmann constant is given. So here, it's just application of the equation NV divided by capital N equal to C E exponential minus EV divided by KT. So here, you need to convert the 500 degrees C into Kelvin. Then you need to find the N first. N. Here, you need to convert per cubic meter. How many molecules in 1 cubic meter of copper? You need to find the N here. Okay, so cubic meter, how many N? How many numbers of atoms of copper in 1 cubic meter? You need to find. Okay, so you move your N to the right, just to write it as a linear equation. Then you substitute the N. Most of the student, they miss out this part. They don't know how to calculate the N. Okay, the N is basically ask you to find how many atoms is it in 1 cubic meter. So N equal to N rho is the density per cubic meter divided by atomic mass of copper. Okay, you take number of Avogadro multiply by the density. In this case, density, this one you find in it should be given. So this one it should be given, or you can find in the appendix at the back of the question. Copper 8.96 megagram over meter cube. This one is in meter cube. So sometimes the question or appendix that you use will be in centimeter cube. So just be careful on the unit. Look carefully which table is given, right? Sometimes you see some kilogram over cm cube. Some table give you megagram over meter cube. This question asks you meter cube. Okay, so substitute accordingly. Number of Avogadro 6, 10 power 23 multiplied by 8.96 mega change to megagram, change to kilogram. Right. So this one we use gram because your unit here, atomic mass is in gram. So we try to synchronize our unit, right? Because your atomic mass for copper is in gram over per mole. So just be careful on the unit. Okay, at the end you find your N. Once you find your N, you substitute all the value. C given. This one, press your calculator, E exponential bracket minus E EV EV here is given. Okay. Okay, EV here is EV is this one, 0.9 EV. We substitute 0.9 here. K, is it K given? K Boltzmann constant is given. T change to Kelvin. You already calculated the N. You can press your calculator, you can find. Give 3 significant figure with the correct index and vacancy over meter cube. So once you find the numbers of vacancies, you can solve for the B. So in 1 meter cube, you have 1.6 10 power 23 vacancy over meter cube. He asks you vacancy fraction at 500 degrees C for pure copper. He asks you the percentage or something divided by this one. Right. So vacancy fraction can be found by taking NV divided by so many 1 meter cube of divided by N, the big N that you just calculate. Right, this one you calculate from 1 meter cube. 1 meter cube have so how many copper atoms? You divide, all right? You will get 1 point something. Okay, so B is a fraction. Fraction don't have any unit. It's a small. It looks small, but in the material science, this one actually is a quite big number. Okay, we have done with this equation. Then we go to the adherence rate equation. So just now, Boltzmann relationship with this one, number of vacancies equation. Now the rate of diffusion now. So developed by this person, it gives you CE exponential Q stroke RT. So Q is activation energy. It can be Joule or in Kelvin, depends on the R value that you are used. Okay, if the R value given is in Joule per mole, then you use Joule per mole. If the R value in the question give you calorie over mole per Kelvin, then you use Kel over mole. Temperature in Kelvin. C is a constant. If it's not given in the question, assume 1. Okay. So C, sometimes we forget to give you. So in your solution, you just write assume C equal 1. And then you substitute value. So this one is from to estimate the thing. So the rate, because this one is in E, so you can write in the log form. You change the log form, so you'll be left hand side will become ln rate. C will become one of the parameter ln C, and this one you move to the front, will become minus Q over RT. So either you remember the first one or the second one. So if you plot the graph by using this one, so you plot y-axis is ln rate, x-axis is ln C, then you have a intersection of minus Q divided by RT. Sorry, you plot mx. In this case, ln C is your intersection. X depends. Sometimes it's temperature, sometimes it's Q, sometimes 1 over R, it depends. So it depends on the type of the graph you see by using ln rate equal to ln C minus Q divided by RT. So if you plot the graph 1 over t in your x-axis, your slope or your gradient on the graph will be q divided by r in negative form. So in negative form, your graph will be slanted to the right-hand side. So you'll see a graph, or sometimes you can put in log 10 also, right? So log 10, if you don't want to write in ln, straight away you can write in log 10 rate C minus Q divided by 2.303 RT. This one is a conversion from ln to log. It's a conversion to ln to log. So it depends on which one you prefer lah. Sometimes you can do in ln, sometimes you can do in log 10 scale. Okay, this one 1 over 2.023 is a conversion. It's a conversion, but we don't go and develop this one. This one from mathematics, we just use and pick from the mathematics and then we apply. Okay, so this is what you see in the material encyclopedia or handbook. So on the left, you will see log 10 reaction, y-axis, y equal to mx plus c. So your c here, when your x 0, your intersection is here. So log 10 c is over here. Then your slope is q divided by 1 over 2.3 r. And you plot 1 over t. So your slope will be q divided by 2.03 r. Okay, so you can find from this graph, you can find the parameter or the slope from the process. This one is you read. So you know that the state in material we have 3 states: solid, liquid, gas. So different. Okay, so these are how the diffusion happen. So in gas, is very rapid. The movement is very rapid, and there are lots of energy there. Liquid is slower than gas but faster than solid. Solid is very hard to move when it becomes solid because of the bonding. So we want to move from solid to gas, you need to give energy to increase the vibration, to break down the structure, then become liquid. Okay, so from solid, liquid, gas, this one you'll see in the graph form when you study phase diagram later. Okay, from atom to make such move, 2 conditions must meet. One, for diffusion to happen, they must have an empty car park there, have an empty adjacent side, means there's the empty space for it to move. And they must have enough energy to jump to another location. There are 2. They must have a space and they have energy. These 2 things. Okay, so diffusion happen in 2 mechanisms: vacancy and interstitial. So this one is a move into the vacancy, motion of the host or substitutional atom, it move to the vacancy, it fill in. So this is called vacancy diffusion. It fill in the space there. Okay, fill in the space. And you see that the movement of vacancy move from below to up. If you look under microscope, you will see black color hole here will move from below to the top. Okay, this one is more on the material energy. So you can see this is a perfect case where you have a perfect sphere and there is a one parking space there. So A want to move from position 1 to position 2, and from the graph energy versus position graph there, to move from 1 to 2, one location means center of the sphere to the center of the vacancy. You need activation energy to jump from 1 to 2. Once it's reached 2, the energy will will move back to the stable or reaction stage. Okay, the next you reach, next you read. Okay, so here, just want to highlight, now you see there's one more column added to the table. Before this, you learn about crystal structure, FCC, HCP, melting temperature, temperature range, and then now you look at activation energy, the Q, or uh, the the E star, the E star. Okay, the rest you read. Okay, so this one is called Kirkcaldy effect. Kirkcaldy effect, you see the diagram on the top and bottom. So what happened is that see, this diagram might not see might not show you the illustration. So basically, it just tell you that the direction of the movement of the hole is the same like what you see on the diagram just now lah. This one I won't ask you lah. Okay, so there's a video here. Okay, you see later, you see this one. This one is a Kirkcaldy effect during a galvanized replacement things. So what you see here is a silver nanotubes become hollow via a nucleation growth as they undergo this one. So you see something happen there. You'll see that this one actually break up. What does it mean? It means that just now you see there's a small dense things and then it become hollow. So you'll see actually the silver nanotubes move up, and then you see the space here actually is the effect because of the silver move out. Then you see the space was filled inside here. Okay, so this one actually is just tell you that um, this phenomena, this phenomena actually it tell you that if you see you are seeing the object actually growing, but in fact is you should be able to understand this one actually the silver nanotube actually moving outside. It's moving from the center to outside, disperse. It's a diffusion. It go outside the environment there. Okay. So here also same. You see the thing growing, actually that one is a phenomena. But what actually happened is that the silver nanotube actually going from one location and go outside, from high density, high concentration to low concentration. It actually sit into another area. Okay. This is called the phenomena of this one, Kirkcaldy effect. Okay. Okay. Now, more important is how diffusion happen. Okay. So before and after, this one is interstitial. Just now is vacancy or substitution mechanism. This one is interstitial. So interstitial means there's alien atoms or impurity, we call it impurity, moving around the space. Okay, moving around the space. So this one, how this kind of case can happen when you have a smaller radius of atoms compared to the host. The orange color size must be smaller than the host. The host is the blue color one. Then only interstitial can happen. Okay. So the rest you read lah. Rest you read. Okay. Now, this graph is important. When you have a steady state diffusion, means the process happen in a very stable, controlled manner. So you look at the top graph. Y-axis is a concentration of diffusion atoms C, of atom concentration 1 to 2. And this one is the distance, x1 to x2. So if your concentration drop from a high point to low point, means the object have moved from position 1 to position 2. Means it original at here, it moved from original position to second position. The concentration of the solution drop from C1 to C2. Okay. Now to make the concentration drop, you need to use up some energy. All right. The rest you read. Okay. So if there is no change of concentration of the solid atoms at this plane for the system with time, then this diffusion is called steady state condition. Okay. So assume over period at plane 1 is C1, plane 2 is C2. This one you read lah. I'm gonna ask you this one. Okay, this is important. So we will ask you to use this equation or the flux or flow of atoms for the steady state diffusion. So when the question asks you to calculate a steady state diffusion, you write this equation, J equal to minus D, the differentiation of concentration. This one is a dc over dx. This one is the differentiation. So it's like dy dx. Your graph is y is your concentration. So dy dx is a gradient. Right? It's a gradient. Okay. So J is a flux of flow of atoms. D is a constant called diffusibility constant. Will be given in the question. So dc dx, this one, it depends on the line, or you need to, you are given two concentration. All right. So how to find the m? Y2 minus y1 divided by x2 minus x1. So to find the m here, to find this value, y2 minus y1 divided by x2 minus x1, you find this value. All right. So J equal to minus D dc over dx. Okay. So the negative sign there is because the diffusion from higher to lower concentration, and this is a negative diffusion gradient. So in this sense, you get negative there. This is also called Frick's first law of diffusion for steady state diffusion condition. So sometimes the question give you direct instruction, apply Frick's first law of diffusion in the analysis, means it asks you to write this equation. You write J equal to minus D dc over dx, then you substitute value accordingly from the question. So the question will give you a statement. Maybe you don't see this graph, but dc over dx is actually y2 minus y1 divided by x2 minus x1. You're finding the gradient of the straight line. Okay, so if the question asks you to use steady state diffusion analysis to find the flux or next flow of the atoms, you write J equal to minus D. dc over dx is a gradient. D will be given. Y equal to mx plus c. In this case, of course, there is a c there, but we not interested to find this one. So if you break the unit, J is atom over meter square per second. So J is a flux or flow of atoms. So how many atoms go through per meter square is the area. So if you draw in a three-dimensional, it's like how many atoms go through this plane, go through this 2D plane in meter square per second. Meter square per second. So D is meter over second. This one you find in the table. D is called diffusibility constant. You find in the table. dc over dx, this one is you'll be given concentration 1, concentration 2, position 1, position 2. Then you find y2 minus y1 divided by x2 minus x1. Then you find the flux. So you'll see this table. You see this table. You'll see solvent and solute. Okay, solvent and solute. Diffusibility is a D, capital D value. 500 degrees C, 100 degrees C. This question come out in last semester final exam. Okay, so what is solute? What is solvent? I use salt and water. If you put salt inside water, the salt is solute, water is solvent. Or you can put solvent as your host. Like for example, if the question asks you the experiment, you calculate diffusion of zinc, the engineer put in zinc inside a copper liquid or copper molten liquid. It means you need to use this row. The solute is zinc, the host is copper. Don't use the wrong one. Some is copper, silver, silicon, especially here. So here, ion, carbon and ion, you have FCC, BCC. So last semester, I asked carbon and carbon in FCC, BCC. Okay, and there's an equation to find the D. So I purposely pull out one of the numbers. You need to calculate the numbers of D. Okay. Okay. So how do you apply? So the diffusion value D here is influenced by a few factors. First, the type of diffusion. If it's a small atoms, okay, it's a small atoms, then you see the numbers a bit different compared to the big atoms. So for example, this one is carbon diffused in FCC. The value is 5. The value is 5 10 power 15 minus 15. But you see, if you bigger atoms, copper diffused in aluminium. Copper in aluminium, the value become bigger. Copper, aluminium, 4 10 power minus 14 meter over second. You see the value change from 10 power 15 increase to 10 power 14. Okay, so it depends on type of the thing. Okay. Number 2 is temperature. So you see there's a value between 100 degrees C and 1000 degrees C. So you compare carbon and carbon, the two value here. Okay, so we already learned that BCC, your atomic factor is 0.68, FCC is 0.74. You see the value. You put in carbon inside FCC and BCC, the diffusion also different. One is minus 15, one is minus 12. BCC, the atomic factor is 0.68, means there's more space there for you to put in alien atoms there. Okay, so FCC, you have a smaller value because you have less space in FCC. FCC packing factor is 0.7, means you use up almost 75% of the cubic space. But here you still have, maybe you still have a few space compared to FCC. Okay. Then the rest of it, so there are type of diffusion, temperature, type of crystal structure, and imperfection present, means these are defect, there's a vacancies. Just now we learned about one equation to calculate the NV. So this one also will affect the numbers over here. The more vacancies, the more diffusion you can do. More parking space you can park. Okay, this one you read lah. So concentration of diffusion species. So these 5 factors will influence the numbers of this one. Why this slide is important? Because once you calculate that one, you need to explain why the value is different. For example, the question asks you MgO and you're given magnesium, oxygen, and nickel. Why these 3 values is different? You need to explain using this 5 pointer. Why these 3 groups here? The value here. Why minus 27? Why minus 32? Why minus 23 at 500 degrees C? And why, if you increase the temperature, the values change? So these are the things. Okay. So this kind of question can come out in section A, ask you about theory, 5 marks or 6 marks, just to test your understanding in diffusion. What can the diffusion affected by what? These 5 points. You don't need to remember all 5, but maybe ask you 3 factor. You write any 3 from this 5 point is sufficient. Okay. So these are the standard table that usually you'll see in your exam. Right. So Ferrum. Okay. So sometimes I will just modify a little bit the table. I will remove diffusion species. I will put as solute. Host metal I'll remove. I will put as solvent. So I'll remove all the sensitive word here so that I can assess you whether you understand what is solute and solvent. Then DO, sometimes I remove, sometimes I do not remove. Activation energy Q, just need to be careful on the constant value. One is in Joule, one is in EV. It depends on Boltzmann constant that is given. If Boltzmann constant give you EV, you use this column. If Boltzmann constant in Joule, you use this column. Calculated value, this one, you need to calculate this one. So usually this value I will remove last semester final exam, I remove one of these value, and you need to calculate the value. Okay, now how do you apply this table by this example 2? So you just seen this one very lengthy statement, and then you solve. You're having a plate of ion. So ion is ferrum. Again, be careful when you see the word ferrum. Why? Ferrum, you have alpha and gamma. You have BCC and FCC ferrum. Okay, and you have alpha. Alpha, here you don't have beta, you have alpha and gamma. So here, ion exposed to carburization. Carburize means you expose to carbon, C, environment. Carbon rich, it give you carbon rich atmosphere. So here you already know which one is solvent, which one is which one is solvent, which one is solute. Okay, so your solute is carbon, your solvent ion, but you don't know which type of ion, right? So it tell you more information at 700 C Celsius. Here, you don't have any 700 here. You need to do interpolation if needed. Okay. If the condition is steady states, you see this steady state means it asks you the J equal to something already. J equal to minus D, then Y2 minus Y1 divided by X2 minus X1 means concentration difference divided by the location or distance traveled. Okay. Calculate the diffusion flux. Diffusion flux means the J equation. Through the plate, if concentration of carbon at position of 5 mm and 10 mm. Of course, you won't see the bracket in the exam. This is just for the info for tutorial. Beneath the carburized surface are 1.2 and 0.8 kilogram. Respectively, assume diffusion coefficient is this value. He asks you to find what? Diffusion flux. When you solve this question, it actually expects you to draw something. First, you know that it's asking you one equation. J equal to minus D, dC, dx. You write this one, might be 2 marks. Okay. D is given. D is 3 × 10⁻⁻11 meter over second. dC is a change of concentration. Right? Now, just now you see the graph is like that. This is C, this is X. So this is 0.1, this is 0.2. This is C1, this is C2. Then X1, X2. What does it mean? You do a cross section of your material. You have 3 depth there, right? You expose your material to carbon, and this one is ferrum. All these are ferrum. At 700 degrees C. So concentration is given at position 5 mm beneath the carburized surface. This is surface. Position of 5 mm. So this is 5 mm. This is 10 mm. You're given concentration. Here, you see 1.2%, not percent, kilogram over meter cube. This one, 0.8 kilogram over meter cube. Now, it should make sense because you don't have carbon if you go deeper. There's no carbon here. So you are actually dispersing the carbon from the surface. So as If you near to the surface here is 100% carbon. Because the carbon landed on the surface here. Then as you go deeper, it will slot in the ferrum gap there. Okay. Now you have C1, C2. You have X1, X2. So put in the calculation. If you understand the equation, you should be able to calculate. Okay. So I'll just give you the equation. Just remember it's negative. It's a negative value, because it's negative gradient. So you put in concentration at point A minus concentration at point B, XA minus XB. So CA is 1.2, CB 0.8, XA is 5, XB is 10. Remember to draw the diagram. Remember to draw the diagram. Sometimes got marks, sometimes don't have marks. But if your answer is wrong, sometimes your diagram will help you a little bit. I will still find ways to give you marks. If you substitute wrongly, I will still help you a little bit. You substitute value, you find the J will be a positive value. There's no negative value of J. Negative is a diffusion. Flux, no negative. Negative is become black hole scenario. Okay, so this is just for your info. Okay, this kind of question come out in last semester final exam. One question. Now you don't have choice. Last year you have 5 questions, 3 compulsory, 2 question 4, question 5, choose one. But start from last semester, you don't have a choice. You need to complete all question 4 questions. You're forced to complete all questions. Okay, we go a little bit more, then we call it a day. Just now you have a first law diffusion. Now, if you have first law is apply for the steady states. Steady state mean you have a straight line. Here we have a straight line equation, y equal to ms plus c. But if you don't have a steady states, then it becomes second law of Fick's diffusion law. You have double differentiation of the equation. Okay, you have double differentiation of the equation. So Ct over, you just take the equation just now. C over T is double differentiation. Dx bracket dc over dx is a differentiation. So on the left is concentration differentiation over time. It's called rate of composition change. You take concentration, look over time, it become a rate of changes of concentration. This is a diffusion rate multiply. Diffusibility multiplied by the rate of change of concentration gradient. Means you pull your D outside, there's a double differentiation of your concentration. How to derive is outside the scope, but is how you apply this equation. Okay. Now this equation only apply when you don't, the question mentioned, ask you to compare steady states. Means steady state, you apply J equal to minus T dc over dx. After that, you do the same, you time differentiate the concentration in x direction. Okay. Now some textbook they use partial differential, but actually it's the same. When you use the limit to 0, you get d over dt. Okay. Now, non-steady states usually is gas to solid, for example. This non-steady earlier. Non-steady means non-steady means the diffusion is independent of time, means the time doesn't affect much. So you have A to B concentration, A to B. If you derive the equation, you see the graph. Just now, the steady state one is straight line. Non-steady is exponential graph. So you see the two line here is not a straight line, it's the exponential line. Okay. So we'll use this solution for Frickel's second laws is the changes of concentration. You just memorize lah. CS minus X. CS means what? Surface. Concentration at the surface minus the X of your interest. This one, second law is to calculate, is to estimate what is the concentration at that certain rate. Okay, then you want to find the time to reach that state, because you want this usually apply in the industry. So you want to estimate the time that you need to reach the concentration that you want. So you take surface minus the distance that you want or your design concentration at that particular depth, divided by the concentration of the surface minus the initial or default concentration, equal to ERF is exponential. E is actually is E power X divided by 2 bracket 2 square root of dt. D is the diffusion rate, the diffusion constant. T is the time in second. So you need to calculate the time to reach the certain design concentration at the certain rate or certain depth. Okay. This one, some textbook give you this equation. Both are same. Both are same. It's only the second one is by comparing the default concentration. This one, it is go into the surface. You see the differences, the differences. And then this one on the right is 1 minus E power X divided by 2 square root of dt. Both also reach the same answer, because both equation most of the time ask you to calculate T. It depends on which one you want to do. So don't confuse between the middle one and the last one. Both give you the same answer. Okay. This one is a semi-infinite solid for constant surface concentration. Okay. So some text will give you this one. Some text will give you this one. So there are two. And we are not interested for the derivation of this equation. Okay, just apply. So this one, C is a surface concentration. CO is initial uniform concentration of the solid, means inside this solid CO. Before you do anything, any process, you have a concentration inside this one. So there's a CO value here. CS is a surface when you already start the process, exposed to the gas or carbon. This is a surface that you want. So CS over here. CO is inside the solid, inside the metals. Okay. X is the one that you want to find. Let's say you want to find the concentration at this area after the X, after a certain time, the carbon go inside or nickel go inside this one at the maybe 1 mm. So you need to calculate the time for it to reach 1 mm at a certain percentage concentration. You use this equation. Okay. We are not interested on derivation of this equation. We are more interested in application of this equation. Okay, the rest you read. Or error function. ERF is the error function. Okay. So ERF, you need to use this chart by interpolation. It's more like statistics, finding the normal graph like that. So for second Fick law, you need to use this graph because you're finding ERF, XERF. Okay, we go for maybe another 10 more minutes. We settle this one, then we call it a day. Okay, now there are two ways. There are two ways on applying this one. Sometimes you're calculating the Z first, then you're calculating the ERF. What is Z? Z is ERF Z. Can you compare this one with the equation? What is your Z? Your Z is x divided by 2 square root of dt, this one. ERF Z is this whole thing. Z is this one. So sometimes you don't need to calculate the Z. Or sometimes you calculate the Z, then you refer to this table. You calculate the T sometimes. Okay. Application will be playing around with these two columns. It depends on the information you have. Sometimes if you have this side, you have the concentration of the object. You have all this value. When you have this value, you use ERFZ value because this one equal to ERFZ. Understand? Understand? Okay, understand not? Okay, so you have all the information of concentration. This side, you do calculation, you get a ratio 0.6 something, maybe 0.5 something, equal to ERFX So you go to this table and go and find the value. For example, you calculate all the concentration ratio, you get maybe you get 0.7707. Then this whole thing equal to 0.07 and your Z value is 0.85. 0.85, you write Z equal to x divided by 2 square root of dt equal to 0.85. You know your x, you know your d, one missing, t missing, then you solve. Okay? Or the question flip. It gives you time, it gives you d, it gives you the distance x. So you have time, you have distance, you have x, you have this value. You have Z value, not ERF value. You have Z value. So when you have Z value, you refer to Z value. Let's say you have x divided by 2 square root dt. You have the time, you have d, you have x. Let's say you have 0.70. Your Z value is 0.70. You go to this table, 0.70. Your ERF is 0.6778. Take this value, substitute here. This whole thing is ERFZ. So 0.6778 is here. Something will be missing here. There are 4 parameters I can ask you. I can either ask you the surface concentration. I can ask you the concentration at that particular X. I can ask you the default concentration of the metals. Then I ask, then I give you, then I ask you the selection of material already. I give you 3 set or 4 set of material. Then you tell me which material is more suitable, or from the table, which is that material. Okay, so let's do a little bit application. Then I think we can call it a day. Okay. Consider gas carburized, again, carburization again, means you inject carbon element to the surface. You're given a steel, 1020 steel, at one temperature, 927 degrees C. Calculate the time in minutes. It asks you in minutes. But usually here everything is in seconds, so just need to convert second into minutes in your final answer. To increase the carbon content from 0.4% at 0.5 mm below the surface. Assume carbon content of the surface is so and so, that the steel has a nominal carbon content of this one. So before you start also, you draw something so that you understand what is the question I want to ask you. Okay, so again, on the one whiteboard, this one is the stable state, steady state, J equal to something. But if the state, you see the question already, you know it's not a steady state because the temperature, because of it asks you different D value and so on. Okay, but of course in the exam we'll give you direct instruction. I will tell you this is a non-steady state. Then you know how to solve already. So this one, you just draw the object. So carburize, C, temperature, right, T, 927 degrees C. Convert this one to Kelvin. This is surface. This is the X concentration. So you have a concentration of surface, concentration of X. This is your X from the surface. And you have a default or before anything, the object concentration O. So if you see the question give you nominal carbon content or default content, means it's a non-steady state question. You don't see this information in the steady state question. Okay. Or if the question want to give you hard time, it will ask you make comparison between assumption that this is a steady state and non-steady state. What is the error between the two? Just additional calculation, maybe another 5 points or 6 points for the calculation. Right? Okay, now you write this equation, Cx minus Cx, Cs minus Co equal to ERF Z. Or you want to correct the full one also can, X 2dP. Just remind yourself this one is Z. Okay, so once you write this one, then you are given, you have surface, content surface 0.9, 0.9% at surface, 0.2% is the internal default concentration. He asks you to increase carbon content to 0.4%. In here, X here is 0.4%. At certain X, X is 0.5 mm. Remember, this one is in mm, while your unit here is in meter square. Remember to use the same unit. Okay, so put in all the information there. It's good that you can draw rather than just, it's important you understand which one and which one. Then you find the Z. You don't have Z, but you have the left hand side. At the left hand side, what is the ratio you get? What is the fraction value you get? Cs minus Cx divided by Cs minus Co. What do you get? 0 point something. What do you get? What do you get? It's the ratio, don't have any unit. So what do you get? Remember to draw. It's good you draw rather than you memorize the. What do you get? 0.6 something, right? 7 something. So 0.7 something. Then you take the x 0.5 divided by 2 and square root the d. D is given. You arrive at one very simple equation. 0.7143 error function ERF bracket 69.88 divided by t terms. So here we ask you in time. So you need to find what is this value. This one is actually, if you already arrive at 0.7143 equal to ERF Z value. So this one you have already go to the table. You need to do interpolation. Go to the table. Where is 0.7143? Is here and here. It's about here and here. Okay. So the value of your Z will be 1.80 to 1.85. But for this module, you need 3 decimal places. So you need to do interpolation. Okay. 0.7 71143. Sorry, it's not 7143 is here, not 0. It's between 0.75 and 0.5, 0.8. Okay. Just now I made a mistake. I thought it's 0.7413. Okay. So it's between here. So it's between 0.75 to 0.58. You need to do interpolation. Know how to do. So I'll skip the interpolation stage. You do interpolation, you get x equal to 0.755. Once you get 0.755, substitute back to the equation. This one. This z equal to 0.755 equal to 69.8 divided by square root of t. T is one is missing. Press calculator, find t. Okay, you get in second, convert into minute. It's 143 minutes. Okay. Anyone you're not sure how to use the table? Okay, example 4 is a flip of just now. Try to see. Maybe I give you a few minutes to solve this one. Same equation, but different table. Example 4. Carborization again. Let's draw carbon. Temperature 927. Carbon content 0.5 mm beneath the surface after 5 hours. (0.5 mm). Calculate content. You don't know what is a carbon X. Concentration X, you don't know. Surface 0.9%. Nominal 0.2% CO. You have the time, 7 hours. Convert into second. So in this case, in the example 14, example 4, you are working from the right hand side. I give you the table, see able you able to find. D is given, D 1.28, 10 power negative 11 meter square S. I'll show you the table. So what is your Z value? You should be able to find your Z value, right? Z equal to 2 square root of T. What's your Z value? What's your Z? Huh? 1. That is 1. Perfect value. 1.00. Okay, Z is 1. So straight away here, Z is 1. So your ERF is 0.8427. Substitute this one for CX minus CX divided by CX minus CO. The CX is missing. Rearrange the equation, you get your CX. Makes sense? Yeah? Okay. Yeah. Okay, I show you the answer. You check. If you ready this one, you are ready for your test 2 already actually. Okay, you substitute. They help you get 1. Z is 0.521. You know how to calculate or not? You know how to calculate or not? How you get 1? In exam, if you get 1, something wrong. You won't get full value in the exam. Okay, you get Z 0.52. You do a calculation. I'll just skip all the steps. You'll get the answer is 0.52%. Okay, just for your info. So you get your X, do interpolation to get the value of somewhere here. It'll be around 0.7. Okay. Okay. So if you compare example 3, example 4, maybe your time you forget to change to second. Okay. So if you compare example 3, example 4, you carburization time from 2.4 hours to 5 hours for these same metals, your carbon percentage are at the same depth 0.5%, 0.5 mm is increased from 0.4 to 0.52%. Just now, example 3 is 0.4%. Then in this one, you increase to 52%. If you increase the hours, maybe another 2 more hours, you increase from 0.4% to 5.5%. Okay, this can be good, can be not good, because more carbon, more brittle. Yeah, metals, you increase more carbon, we become more brittle. It can handle compressive stress, but not very good in tensile. We cannot pull. You pull it, it break, or you torsion, also break. So you need to control the percentage of carbon in metals. Okay, so if no question, example 5, you go and see. Right, your homework, go and see. Example 5, same, something missing. Okay, this one you read. Application or industry, how they make parts become stronger. So these are the intersect of the object. You see the surface, this one becomes stronger surface, especially the gear component. This one, if you're interested, go and see lah. So this is a component in the, I think in the aircraft. So you see there's a dark gray area here, is a strengthened mechanism using carburization process. Go and read. This one, you go and sort of see what is the doping. They do wafer. This one also you read. It's actually the same things. Go and read example 6, just substitute value. Read effect of temperature. Also same. Look at your graph. Example 7, go and read. Okay, go and read. This one, example 7. Example 8, also read. 9 is design question. This one will be your final exam standard. Go and read. Go and read. So all the steps are there. Okay. So with this, we conclude chapter 5. Okay, go and read. Okay, your